Welcome once again to this lesson on Aspen Plus. Today we'll be looking at heat exchangers. In Aspen Plus, we would see how to simulate them and use them for sizing or designing heat exchangers. There, we'll look at the Heatex model and its details. So generally, heat exchangers are devices that are used to change the temperature or phase of a stream. A lot of the time, we would need a high temperature stream for some process. Maybe for a reaction to occur, we need to heat a certain stream before feeding it to the reactor. We might have to cool something to before sending it to a separator for various reasons, right? We may want to change the temperature of the stream, and the devices made for that are heat exchangers. And heat exchanger is a general term for heaters and coolers, heat exchangers, and then vaporizers and condensers. The heaters and coolers are made specifically for changing the temperature of a stream using a utility. A utility can be electricity, it can be electrical heating, it can be steam, it can be fired heat. Once a utility is being used to only change the temperature of a stream, the equipment involved is a heater or cooler. In other cases, we may contact two process streams on the same plant to exchange heat between them, and those are heat exchangers. And so they exchange heat between two process streams on the same plant. And then vaporizers and condensers are made specifically for phase change. Right. So Aspen represents these equipment very well. There are many options for working with heat exchangers in Aspen Plus. We've already seen how to use heaters and coolers in many of our tutorials so far or our lessons. We are going to focus more on the heat exchangers. So we'll attempt to solve this problem in Aspen Plus using the Heatex model. So we have a Freon 12 at a flow rate of 12,000 kilograms per hour, and we want to heat it from 250 to 300 Kelvin. Ethylene glycol is available to do that work, and is desired to use a typical shell and tube heat exchanger. The minimum temperature approach has been specified as 15 Kelvin, and the tubing, the convention for the tubing or the tubing standard has also been specified. So let's dive in and attempt to solve this. So we add ethylene glycol. Next, property method. So we choose NRTL, and then head to the simulation environment. So the first thing we look at is the design equation for a heat exchanger, right? And you see that in order to size a heat exchanger, that's to determine the area. It's related to these parameters: the heat duty, and the heat transfer coefficient, and the logarithmic temperature difference, right? So since we have the temperature difference, we need the heat duty or the amount of heat the ethylene glycol stream needs to supply in order to raise the temperature of the freon to the desired point. Right? So what we are first going to do is we're going to use a heater to determine that duty. Come to the model palette, select heater, and then add a material stream. Freon in and out. want to specify this. Freon is coming in at 250 Kelvin. 8 bars of pressure. And the mass flow rate. You want to raise the temperature to 300. And the pressure drop is 0.1. We can run our simulation now. Now that we are done, first we have to go back. We didn't choose the right. So it should be dichloro-difluoromethane. You can find it easily by just specifying the alias in the component ID. So this should be the freon. Come back to the simulation environment and run the simulation. We can look at our results. And then we see the heat duty from the heater block, the results for the heater block. Now that we've done that, we go back to our flow sheet and then we add a heatex block. So delete this. That's the easiest way. Then bring the heatex block. So the heatex block is a rigorous heat exchanger. It's capable as a capable rigorous heat exchanger, and it requires 4 streams. The hot side is a stream that requires heating, or the cold side is a stream that requires heating. So it's a cold stream and it needs to be heated. And then the hot side is a hot stream that needs to be cooled. Right. So the stream we are using for heating goes to the hot, and the stream that's being heated is the cold. So this is the MEG stream. Right. So once you've done that, we need to find the right flow rate of ethylene glycol for this work, since we were not given in the problem. So since we know the duty, right, and the heat lost by the heat gained by freon is the heat lost by ethylene glycol. Right, so based on MCPDT, we can use the heat capacity of MEG to find the mass flow rate required, or to estimate the mass flow rate required, and that has been done. See that the required mass flow rate is 4,843. So we start from there. Three bar 370 Kelvin, and it's just MEG. Right. And the next thing is to go to our block and choose to specify the heat duty, the exchanger's duty, right, which we've already estimated as 180.049 kilowatts. The temperature approaches 15 Kelvin. It's temperature difference, so we could have stayed at Celsius. Then we can run our simulation. Once we are done and we view the block results, we see that the outlet temperature is not exactly as desired. It should be 315 Kelvin. Right? So we are supplying too much heat. We can go back and reduce the mass flow rate of our heating stream, and you find out that point is 4532 kilograms per hour, and that should give us the desired output, 315 Kelvin. We can come to the exchanger details and we see the heat transfer area or the exchanger area, right? And the coefficients and all. Once we are done with this and we want to size it rigorously now, right? We want to, this was a shortcut approach. So we want to size it rigorously now by going to the tab or the exchanger design and rating feasibility panel on your dashboard up here. And when you click on that, it brings you here. You can convert to rigorous. Right? So you can size interactively or use a template, assuming there was an already designed heat exchanger. So in this case, we don't have one, so we choose to size interactively. And the EDR console should be open for you. And we have sizing parameters, which will come to process parameters as well. And according to our problem, the allowable pressure drop was 5 psi on the cold side. Right, and that's all we need to indicate. We go back to our geometry, and based on our tubing specifications, we have to size. We choose to size. We're given carbon steel. We choose to use tube dimensions of 8.071. The length should be 143 inches, and then the baffle spacing 2. Right, the number of passes should be 2, and then we have one shell in series and parallel, just one shell. Once we are done with that, we can choose to size. The parameters are in the reference material used, data values for this place. So once the results are available, we can go there and then we see we have the temperature profile for the streams, right? And also we have the side view or the sitting plan for the heat exchanger. Okay, we can also go and have a look at the tube layout based on the pitch we chose. Right. And if everything is fine, we go to accept the design. Right. So once we have done that, we come back to our block and we go back to the EDR environment. We see all the available warnings and conditions for our heat exchanger, and if you click on it, it should detail the warning for you, the details of that problem. We could have also designed this using the Heatex block, and we can use it to swap the position of the streams based on which is on the shell side and which is on the tube side. So we come back here and we choose rating. We have the exchanger duty, and then we change the model fidelity to shell and tube. And once we are done, we can size the exchanger, and this should take us to the same point. Right, it brings us to the same end, and we can do as we did before. So that's it on heat exchangers in Aspen Plus. We would meet again for pressure changes. Thank you.